So we're going to determine the rates of chemical reactions. Now, there are key factors that affect the rate of chemical reactions. Now, note that we're talking about the rate. So we're talking about how quickly they occur. And we'll need to go into this into more detail over time, in the later modules and so forth. But right now, just remember that the key factors are the temperature, the concentration, the surface area, and if you have a catalyst. So the things that mainly affect the rate of chemical reactions are temperature, concentration, surface area, and catalyst. You may see in other books and so forth, other things like, agitation, stirring, mixing, particle size, and so on. They can all sort of be related to certain things like surface area and so forth, and we'll talk about them then. But as far as, in an exam that you're given, these are the answers you want to give: temperature, concentration, surface area, and catalyst present. Now, if the temperature goes up, then the reaction rate goes up. And you can probably see this in the same way that, for example, food decomposing and going off is a chemical reaction. And if you put the food outside in winter, it goes off, but not as quickly as in summer. And in a way, you can think of that as an indicator that, well, in summer, the temperature is higher. When you leave the food out, the chemical reactions that break the food down go faster, and the food goes off faster. And that's also why we have a refrigerator. We have a refrigerator to put the food in to bring the temperature down, which will reduce the rate of the chemical reactions which break the food down, which means the food will stay, in our opinion, fresh for longer. So that's one example of temperature controlling the rate of reaction, or at least affecting it. Now, concentration, which has a symbol like this, right? The concentration. If we increase the concentration, then quite clearly the reaction rate will increase. You've probably done experiments before where you've got reacted, metals with acids, particularly with the recent reactions we've been talking about. And you can just try it with the same metal and the same acid, but one is concentrated of the acid and one is dilute version of the acid. The concentrated version will probably bubble a lot faster compared to the dilute version. And that indicates that the reaction rate is proceeding faster in the concentrated version. You can do a similar experiment to see what the surface area would do. So if we have a big chunk of metal versus the same amount of metal but cut into lots and lots of small pieces, and you put those small pieces in instead of the big chunk, you'll often find that they disappear a lot faster and they react a lot faster. Now, you go camping, so this might make more sense to you. If you go camping and you want to start a fire, you don't use a log. You use little twigs and little leaves. Now, if I have twigs and leaves, obviously they're smaller too, but if I have lots and lots and lots of twigs and leaves versus one log, well, which one burns faster, right? Even if I have lots and lots and lots and lots and lots of twigs, which make up the same amount of mass as one log, you'll probably notice from your campfires that your twigs burn a lot faster. And that's because the surface area is greater. And so if you want to, burn a lot of wood, just try and get lots of little pieces of wood. But if you want the wood to last for a bit longer, then you maybe grab a log. Catalyst, well, we've talked about it a little bit before for your assignment. But basically the idea of a catalyst, if it's present, then the reaction rate increases. And that's entirely the purpose of a catalyst. That's what a catalyst is meant to do. We'll also talk about it in a bit more detail as we go along. But these are the 4 factors, and you need to know how they affect it. Number 1 is temperature. As temperature goes up, reaction rate goes up. Number 2 is concentration. As concentration goes up, reaction rate goes up. Number 3 is surface area. As surface area goes up, reaction rate goes up. Number 4 is catalyst. If you've got a catalyst present for your reaction, then the reaction will go up, compared to if the catalyst is not there, because that is the entire purpose of your catalyst. Now we'll be examining why these things happen. So, why does increase in temperature increase reaction rate? Well, you won't be doing this in thermodynamics in your physics, but let's just quickly sort of explain it in this way. As temperature goes up, as you increase the temperature, then what happens is that there is more thermal energy available.
Yeah.
And basically that means the particles have more energy. And in simplistic terms, if the particles have more energy, think of it as cars that are moving around faster. They've got more energy when they hit each other, right?
Yeah.
So therefore, the collisions will be more energetic. Now, you need to remember that for a chemical reaction to happen, you need to actually break the bonds in the first place. And the bonds are broken by having the collisions collide successfully with enough energy. So, because the collisions between particles are more energetic, they have more, therefore, there is a higher chance, right, that there are more collisions with enough energy. Basically, that means more collisions have enough energy to break the bond. And therefore, the more bonds that get broken, the more that can form. And therefore, you know, there is a higher reaction rate. So this is the basic idea. You know, there's a more detailed version if we're going to look at the distribution of, you know, if we look at activation energy and Maxwell-Boltzmann distribution and so on. You can look at those in more detail as we proceed through this topic. But firstly, this general idea, as you make the reaction go through at a higher temperature, always reaction rate increases. And the reason the reaction rate increases is simple. There is more energy around, which means the particles have more energy, which means they'll hit each other with more energy, which means they'll more likely break the bonds, and it'll more likely to happen. All right. So basically think about it as if, okay, do you think more people will buy stuff if there's lots of money around? Or,
Yes.
you know, yeah, same idea, right?
It's just what's it called? It's a collision theory.
Yeah, it's collision theory. So there are more details behind it that we can introduce with Maxwell-Boltzmann and so on. But let's start with the very general idea for the moment. It's a bit like this, right? If everyone has lots of money, they're more willing to spend. They're more able to spend and buy stuff. Whereas if no one has money, then, you know, no one can buy anything. And so temperature is like the money. Everyone in general every particle is rich. Every particle has energy. So it's happy to spend it because a reaction needs this energy input. And so it's more likely to happen. Yeah?
Yeah.
Now, the next thing we want to consider is, why does concentration affect reaction rate? And more specifically, let's consider, why does increasing concentration increase reaction rate? So we need to think of what concentration means. And you might remember from before that concentration is, the molar, the amount of moles, which is the amount divided by your volume. Now, this might also be important to point out now that really, for the most part, concentration really, for the things you're doing, mostly only affects solutions and gases. And it doesn't really affect solids and liquids. And that's because for a solid and liquid, we say that the mass is the amount, the volume is unchanged for a solid or liquid. And the amounts, once you know a certain amount, you've got the certain volume. So the concentration won't really change when you've got a solid or liquid. So it doesn't really matter, right?
Yeah.
Whereas if you've got a solution, the volume, so say salt water, how salty it is depends on how much water you added. The volume is dependent on the solvent, mostly. So you can basically you can change that volume all you want, and that will very dramatically change your concentration. So that's why for solutions where the volume can change very easily for the same amount of solute, we need to consider the concentration, because it's the solute that is reacting in our reaction, not the solvent usually. And similarly, gases are important as well, because we know gases have a certain, the volume is dependent on the container, and the moles is just the moles. And so we can put the same amount of gas in different containers and change the concentration of the gas. And so that's why concentration is a concept that applies mostly to solutions and gases, and we don't really need to worry about it when it comes to, solids and liquids. So keeping that in mind then, that this is mainly for solutions and gases, and keeping in mind what concentration means, it's the sort of amount of something per unit volume. You can think of it as the density of that substance. Not in terms of the mass, but I mean how likely it is for you to run into a particle.
Yeah.
So think of it like population density. Because I could have, if I have a, small country and a large country, and if I have, a low population and a high population. So think of this population kind of as the amount of people, and think of the country, sort of the area, as the volume sort of idea. So if you've got a small amount of people in a small country, well, you don't really know. This could just be, average or moderate. It's hard to say. And you've got lots of people in a large country, and again, you don't really know. That's sort of moderate. But if you ever get a situation where you've got a very small population in a large country, so maybe somewhere kind of like Australia, then you get the idea that this is low density, right? People don't live close together.
Yeah.
If you've got a very, Australia might not be the best example, but I don't know, maybe Greenland or any sort of area where that. Whereas if you've got a fairly large population for a small country, it's the ratio between the area and the amount. So for example, like Hong Kong, Singapore, and so on, then this is going to be a very dense area. Does that make sense?
Yes.
So these are situations where you've got like high population density, which would be analogous to our concentration. And this would be a low population density, which is analogous to our low concentration. So let me ask you, if you randomly put someone in Hong Kong, right? Just randomly put someone in Hong Kong and walk around, are they likely to meet someone else?
No.
Why not? There's lots of people in
It's
Hong Kong,
too
right?
dense.
Yeah, so are they likely to meet someone else? If it's very dense.
Wait, oh, yeah.
Yeah, I mean, it's very dense. You're going to see someone, right? It's very hard not to see someone, right?
Yeah.
But like, I mean, anyone. I don't mean your friend in particular. I just mean like to see someone.
Yeah.
Whereas if you're stuck in the middle of the desert with a very low population density and just randomly put you somewhere in the desert, is it likely you'll see someone and run into someone?
No.
No. So there's a very low probability then. Does that make sense?
Yeah.
So you can see that basically high concentration means that you've got a high probability of collision. Does that make sense?
Yes.
And if you've got low concentration, you're going to have a low probability of collision. Now, of course, a collision doesn't mean it's successful, but to have a reaction occur, you need to collide in the first place, and then you need them to be successful. So if you're likely to collide, then that means you'll get more successful collisions because you just got more collisions in the first place, right? And if you've got a
Yes.
low probability of collision, then you'll be fewer successful collisions. Does that make sense?
Yeah. Yeah.
Good. The next thing we're going to focus on is why does surface area affect reaction rates? Now, it might be, again, sort of useful to point out what surface area is. So surface area is sort of the area of the surfaces of an object, which is really a concept that really mostly applies to solids. Because gases, I mean, it's not really a surface area of a gas. I mean, what surface are you measuring, right?
Yeah.
For a liquid, I mean, there is a surface area, but I mean, it's not particularly all that useful too much. It's really mostly about the solids, right? A solid is what's got a surface area. And, you know, the key thing, again, comes back to collision. Because think about a big box, right? If you've got something in the middle of the box and you're trying to get to the middle of the box, can something outside get to the middle of the box?
No.
No. So for example, let's say this is iron and oxygen wants to react with iron. The oxygen needs to meet the iron, right?
Yeah.
Can the oxygen meet the iron? Can the oxygen meet the iron in the middle of the box?
No.
No, because it's got all these iron in the way. So really, which ions can the oxygen meet?
The surface.
Exactly. So really, remember, to react, the particles need to collide. So for a solid, at least to start with, only the particles on the surface are available for collision, right?
Yeah.
So I think I went through this with you earlier when we did your assignment, but think of, and you know, you mentioned you play games. So think of this as, you've got a melee sort of, everyone has swords, right? Sword people can only fight people next to each other, right? You can't go, hey, I'm half a screen away, I'll just like attack you, right? Not with a sword.
Yeah.
So the amount of people fighting at the same time just depends on if you've got a little point where there's only one person standing there, doesn't matter how many people stand behind that person until that person, wins or loses, you can't get more fighting going on. Does that make sense?
Yeah.
So therefore, for solids, this is the surface area. So the surface area tells you the quantity available to react now per unit time. Now, how can you increase the surface area? What are the ways we can increase the surface area? If I've got a big block of iron, how do I increase the surface area?
You add more.
Well, maybe, but that's just, what if I don't add more? So I could add more blocks. What if I don't want to add more blocks, then what I could do is, to change the shape and so forth, but basically, let's say we cut up into smaller pieces, right?
Oh, yeah.
Because if I've got one block like this, but now I cut it up, like I just make one cut like this, then this is going to give me two pieces, which will have, my original section here, that doesn't really change this, but I'm going to get this extra surface, right? That's extra compared to before. And similarly, my piece here, none of this part will change on the right, but I'm also, that part is extra. Does that make sense?
Yeah.
So we can see that the more cuts we make, the larger the surface area. And so another way to think about it is that the smaller particle sizes, which result in increased surface area, will therefore result in increased reaction rate. Does that make sense?
Yes.
Now, a very similar, but not entirely the same thing, is if you've got a solution with a suspension or something, sometimes we also talk about mixing the sort of reaction mixture. So often we talk about mixing the reaction mixture as well. And if we mix the reaction mixture, then what we end up doing with that is that we ensure it doesn't sediment. And if we ensure it doesn't sediment, then again, we are, increasing the surface area. So all of those things help to increase the rate of reaction, essentially by increasing the surface area.
Yeah.
And lastly, we said catalysts also increase the surface area. And that really just comes back to, sorry, they don't increase the surface area, increase the reaction rate, I mean. So these are increase the reaction rate. Now we will talk about a bit more about how they work, but for right now, what we're basically saying is, what is a catalyst? A catalyst, by definition, is a substance which, is not a reactant, so does not get consumed in the reaction, so it doesn't get used up. And, by definition, it increases the reaction rate. So if a catalyst, by definition, is something that would increase the reaction rate, or quite clearly, if you've got it, the reaction rate goes up. If you don't have it, then reaction rate goes down. Or, well, it doesn't go up, shall I say, right?
Yeah.
And of course, but we need to, just in case it's not clear, a catalyst is, specific to a reaction. You can't just go, hey, I've got a catalyst, I'll just add it to whatever I want and the reaction will go up. No. If you've got one particular reaction, then there are only certain things that will speed it up. it's not gonna be like, oh, I'm gonna take this catalyst from this reaction and just dump it into the other thing. They won't all work. All right. A catalyst needs to be like is specific to a reaction or reaction type, right?
Yeah.
You can't just go, hey, I've got a catalyst. This thing works for everything. I can just dump it into anything, any reaction. That doesn't work.
Okay.
Now, what might be worth considering is, well, scientifically, how do catalysts do this? How does? I mean, we've said a catalyst is something that increases reaction rate. That's great. And you can come up with examples of this. So a catalyst that increases reaction rate. So for example, in your assignment, it was your contact process, and that was vanadium oxide, right? We basically said if you added that thing, it will make it go faster. If you didn't add it, it wouldn't go as fast. You know, if we talk about other things like photosynthesis, we say it's chlorophyll. And you know, we can keep listing examples. The question now here is, how does it do it?